Hi, I'm Daniel Ting, and welcome to my talk on adaptive threshold sampling. So the fundamental problem that we want to look at today is how do you draw a good sample when the sampling probabilities need to adapt as you see more data? And there could be many reasons you encounter this. First of all, your data may be streaming. You may have budget constraints on your sample or particular target error rates you want to achieve, or you may want to give your sample some sort of time decay behavior. And the challenge is that when we have these samples which are being chosen in this adaptive manner, they become dependent on each other. This makes the sampling probabilities and expectations often intractable to compute. And so you may not even be able to check whether an estimator is unbiased in a computationally efficient way. And if you don't have a good tractable estimator, your sample is essentially worthless. And it's actually quite easy to see examples of sampling designs for which it's difficult to compute these tractable estimators. For example, if you simply take a weighted sample of size k drawn without replacement, one of the simplest designs possible, then what you find is that if I want to calculate the probability that any particular item is included in the sample, this requires summing over sequences of length k, which quickly becomes intractable, even for modest k. So what we proposed is to look at a class of sampling methods, which we call adaptive threshold sampling methods. We propose a framework to build and compose sampling schemes that are able to adapt as more data is observed and naturally have good estimators associated with them. In particular, we want to answer the question, when can an adaptive sampling scheme be treated as if it were fixed? That is, that the probabilities were fixed in advance. And so what we'll also be able to see in this talk is that this framework will also allow us to easily derive new sketches and improve old ones. So what is an adaptive threshold sampling scheme? First, we looked at a fixed threshold one. In a fixed threshold sampling scheme, each item has a particular fixed threshold tau I, which is specified in advance, and draws a random priority Ri from some distribution Fi. The item is included in the sample if Ri is less than tau I and discarded otherwise. And it's easy to see in this case that each item is sampled independently with probability Fi Ti, or tau I. An adaptive threshold sampling method simply takes this threshold and makes it a function of the data and priorities. In this case, we'll still run into some computational problems if I wanted to compute an exact inclusion probability, but we'll find that in many cases, we can actually still treat it as if it were fixed, as if the threshold were fixed. So let's look at an example of when an adaptive threshold sampling procedure helps. So if the problem is to draw the best sample of size k for estimating some sum or subset sum, then there's a well-known method called priority sampling by Duffield et al., where each priority is drawn uniform 0 xi, where xi is the value of item I, and it chooses an adaptive threshold to be the kth plus 1th smallest priority. It turns out this essentially draws a probability proportional to size sample, which is a sort of optimal sampling design for this type of problem. And what they show is this sort of amazing property, even if the paper isn't cast this way. It shows that the off-the-shelf unbiased Horvitz-Thompson estimator for fixed thresholds is still unbiased for the adaptive threshold. That is, I could take an off-the-shelf estimator for this design where you sample items independently from each other and apply it straight up to this adaptive threshold. And that's great, but what if we look at a small variation of the problem? Suppose instead of finding the best sample for a given sample size, we find the best sample given a particular memory budget. In this case, priority sampling can be extremely wasteful if the item sizes differ very greatly, since it must choose a k which is conservative. And now the question arises, how do I choose an appropriate adaptive threshold? And once I choose this threshold, is the Horvitz-Thompson estimator still unbiased? So let's look at how we can get unbiased estimators and build thresholds which will provide unbiased estimators. There are three main ideas to this part of the talk. One, which is that any estimator is necessarily restricted to the set of functions which are functions of the sample. And we only need to evaluate expectations on this restricted set. The second idea is threshold recalibration. So what we do is for every expectation that we need to compute, we find that we only need to compute an expectation relative to a small number of indices, and we can compute an alternative thresholding rule where the desired expectation on this small set of indices is easy to compute. And finally, the third idea is threshold substitution, where we look at conditions where the alternative threshold is actually equal to the original threshold. In these cases, the alternative threshold can basically be treated as if it were fixed on this restricted set of functions, and we can just use an unbiased estimator for a fixed threshold. So we'll only talk a little bit more in detail about the second idea, that of threshold recalibration. So in this, how we recalibrate the thresholds and constructively build an alternative threshold is that we take the original thresholding function, and we want to construct a threshold tilde tau that is independent of the priorities of interest. That is this subset of indices lambda. And once we do this, the conditional inclusion probability then becomes easy to calculate because tilde tau acts as if it were a fixed threshold. And we can build these alternative thresholds by first fixing all the priorities which are not in this subset of indices lambda, varying the priorities that correspond to lambda, and taking the minimum threshold that you see over this when we try out these different priorities. And to see an example of how this works, we can look at a bottom case sketch with k equals 4. So in this case, we have priorities which are scattered on the unit interval and a threshold tau, which is equal to the fifth largest priority or fifth smallest priority. If I move priorities which are already smaller than tau, then tau will either stay the same or it will become bigger. But either way, the minimum threshold that you see is the same as the original threshold. And so you have this property that the alternative threshold is equal to the original threshold. Now we can look at the fixed memory budget case. So the same kind of threshold recalibration property works if I take tau to be the largest priority that keeps the sample within the budget. And so what we see here is that we have this argument that we have an alternative threshold which can be recalibrated and substituted. And so the Horvitz-Thompson estimator is still unbiased. So we were able to generalize this priority sampling fixed sample size case to a fixed memory budget case. Now let's look at some other applications. First, we'll look at trying to use this method to improve an existing algorithm. So we'll look at the sliding window sampler by Gamilla and Lerner from Sigma 2008. And the goal is to maintain a uniform sample of points for a sliding window of length delta. And in this case, items are arriving at some rate which may vary over time. In this algorithm, each item draws a uniform 0-1 priority. You maintain a bottom case sample for the current window, and items can be kicked out of this sample either because the threshold is decreased, or you move, or a sample expires, in which case you move that sample into a buffer for the previous time window. To get a uniform sample for the current sliding window, you then take a bottom case sample of both the current and expired samples and return only the current samples. And we can recast this as an adaptive threshold sampling scheme by noting that by maintaining a bottom case sample for the current window, we essentially assign each item a threshold. By moving expired samples into this buffer, it provides a way to reconstruct all the thresholds for items in the current window. And we can replace this third step of taking a bottom case sample because this bottom case sample is actually choosing a suboptimal threshold. So using the framework in their paper, you find that a better threshold is simply to take the minimum threshold of all the current samples. And what you find is that we can look at the sample sizes as items arrive. So in this particular case, we have items arriving at a constant rate, except for a spike between 0 and 1. And when items are arriving at a constant rate, we find that we're able to recover twice as many samples out of exactly the same sketch. That is, we don't use any additional information. And furthermore, when there's a spike, we're able to recover much faster. And so basically, our sampler is always able to dominate the Gamula and Lerner approach, even though we've changed nothing about what's being represented in the sketch. We can also solve new problems. For example, we can look at the top K problem. So this is very similar to the frequent items problem, except that in the frequent items case, you're tasked to find all heavy hitters. That is items with a frequency known to be greater than n over m, where m is the sketch size. Whereas in top K, you're tasked to find the largest K items, and you don't necessarily know anything about their frequency. So if you were to take a traditional sketch for the frequent items problem, such as measure grease, space saving, count min, then you would essentially need to know the frequency of the top K items to solve the top K problem, which is an unrealistic assumption. What we can do is to try to take one of these frequent item sketches, a randomized version, and now try to adaptively adjust the size of the sketch. So if each sample item consists of the item itself, a threshold for when it entered the sample, and a count of the number of times it appeared after the sample, then we can do the following. We could note that for these randomized frequent item sketches, there's an important distinction. They essentially form two classes of items. One, which are the heavy hitters, where the counter is going to infinity in an IID stream, and then everything else, which will basically have the same estimated count of roughly 1 over tau, and have a counter which is approximately 0. And so if we find that at any point in time, we have fewer than K heavy hitters, then we can keep tau the same. This will sample more items and give more opportunities for already sampled items to accumulate counts in their counter. And then this will eventually result in more heavy hitters. On the other hand, if we have too many heavy hitters, then we can increase the threshold to basically sample one item to remove. And eventually a heavy hitter will become one of these sort of normal sampled items. And if we look at how this does on the top K problem, we can look at, for example, a Pittman-Yor 1-beta preferential attachment process, which is able to generate both light-tailed and heavy-tailed behavior. And so what you find is that in the easy cases, both frequent items and the top K sampler do very well, return very low errors. But when the frequent item sketch is size too small, then the error quickly becomes extremely large. On the other hand, the top K sampler is always able to return the top K with very few errors. Furthermore, when the top K problem is very easy, the top K sampler is actually able to adjust the size to be even smaller than the frequent item sketch. And likewise, it's able to adjust the size to be larger whenever necessary. The third part of our paper allows us to deal with a wider range of estimators and thresholding rules. The disadvantage of the threshold substitutability framework is that it really only justifies the use of unbiased estimators and does not justify the use of a wide range of consistent estimators. These include estimators such as those for linear regression, sample kurtosis, maximum likelihood. It also restricts us to a certain class of thresholds, particular thresholds that can be recalibrated and which are substitutable. In this case, we consider a hypothetical set of thresholds, fixed thresholds, and we ask what would happen to the estimator if the threshold were equal to some particular value. We show that this can be treated as a random process, and in particular that it converges to something called the Gaussian process. The important property of Gaussian processes is that they have continuous paths. So what this allows us to do is it allows us to show that if an adaptive threshold converges in some sense, then a consistent estimator for fixed thresholds will also be a consistent estimator for an adaptive threshold. It also allows us to take error bounds for estimates using fixed thresholds and put them together with error bounds for the threshold itself to form a combined error bound for the adaptive threshold. So just to recap, we propose a sampling framework that allows the sampling distribution to adapt to the data and which naturally yields good estimators. We consider 3 parts to this framework. One, which allows us to build adaptive thresholds that are able to yield good unbiased estimates. We demonstrate several novel applications of the framework, and we show that we can address an even broader class of thresholds and estimators. Thank you for your time.